Hello everyone, so I'm Steve Lau. No I'm not, I'm Steve Lau. So we're going to change tact a little bit here, and we're going to look more around a little bit lower down and some of the components that AI relies on. So can I just have a show of hands, how many of you are using GPUs today? Okay, quite a few. How many are you planning on using GPUs if you're not already? Okay, so most of you, this is good. And how many of you struggle with getting time on your GPUs and getting availability of your GPUs? A few of you? Okay, cool. Well, hopefully we can help those few people. But no, I'm going to talk through a couple of things first. So the first component that we're going to be looking at is the challenges, so what we see in the market. Hang on. There we go. So we're going to look at the challenges first, then I'm going to give you a bit of an overview about Run AI, who we are, what we're doing, and then we're going to look at the example. What's going on there? But we're going to look at an example flow of what it actually looks like within our UI, and then obviously a nice summary and some questions, hopefully. So if we have a look, what are the challenges? So one of the things that we found from talking to a lot of organisations who are thinking about AI or currently delivering on AI is that there's a big focus on the tip of the iceberg here. It's all of the things that you guys will be utilising, used to, your MLOps tools, everything that you're utilising from building a model, training a model, to delivering it in production and inferencing. And also there's a big focus underneath on the infrastructure side of things. But what's actually missing is this piece in the middle, and how do you actually deliver that infrastructure to you guys so it's nice and easy to utilize, and ultimately as well give you that availability of these scarce resources such as GPUs. And essentially the three components that we see as part of that is obviously sharing to compute dynamically. You know, it's very easy to just have a spreadsheet, and we see a lot of organizations using this. It's a spreadsheet, and you as a researcher will be given a GPU for X amount of time to perform your tasks on. But the reality is, in that scenario, it's quite inefficient, and it's very rare that you will always be utilizing that GPU during that period. So there's times where that GPU sat around in an idle state, and it means some other researcher who might have stuff to do has to wait until they have access to GPUs. And so sharing compute dynamically is a big challenge out there today, and it's a big prohibitor for AI in particularly enterprises, but in every organization. The other thing is, there's often multiple projects going on in different organizations, and they're all using different tools, and they have different users, and they all have different needs. And maybe at the different stages of the AI lifecycle, maybe some are still building, some are training, maybe some have got models in production. And having infrastructure configured in a way so that it can support all of those in a single platform is a big challenge today. And then the last piece is, as I said, orchestrating that full AI lifecycle. I think what we've seen is there's a lot of interest in AI, a lot of people are investing in AI, but a lot of people haven't quite figured out how to get the value out of that AI for their organization. And as a result of that, you end up with organizations looking at their AI investment. They've invested a lot of money into their resources, and they're maybe not getting much out of that right now. And so it doesn't look like a great return on investment for them. And a big part of that is because ultimately GPU resources are not readily available, and therefore you end up with a very slow time to market for your models and things like that. A good example, I guess, is if you look here, you've got 4 different workloads going on, and they've all got a different footprint from a GPU perspective. But you can see that there's a lot of these where you could actually merge them on top of each other. But actually in most organizations, this is exactly how their GPU utilization looks. And you end up with these long periods where nothing's happening. And what you really need is something that can schedule these for you and fit them all together so that everyone's happy, everyone's getting the time they need on it, but you're getting your GPU utilization to a much higher level. And that's when you can then obviously get models developed quicker, trained quicker, and ultimately into production quicker and delivering value quicker. And again, what we see in the marketplace is actually around, on average, 20% utilization thereabouts on GPUs. where Run AI isn't in use. And we actually have an open source tool that you can freely go and try called RM Top. And you can run that in your environment. You can see exactly what level of utilization you have. But that is obviously not a very high figure, and is a big prohibitor for all of you guys, right, in doing what you need to do. And that's really where Run AI fits. So we've been around since 2018. Product has been around for about 3 years now. We've got numerous customers. You can see some of the UK-based customers we have here. We've been recognised by numerous organisations. And really what we're doing, as I said, is bridging that gap between your infrastructure resources, which as researchers, you don't want to touch any of this. You want it available, you want it accessible, but you don't want to touch it. You definitely don't want to touch Kubernetes. We sit on top of Kubernetes. And we're then bridging that gap between the tools you're using and the infrastructure below it, making it nice and easy to consume, but much more readily available, and ultimately, from this side of things, increasing the utilization down here. As I said, key thing we're doing is abstracting all of the complexity, but we're also not going to dictate what you're using above. So Run AI has an integration policy. Any of the MLOps tools that you're using, you can continue to utilize. We're not trying to change that. We're trying to fit in seamlessly to enable you to have easier access to these resources and easier access to actually deploy things as well without having to touch infrastructure and things that you don't want to touch. So one of the things that we do is around our scheduling. We have the concept of quotas in Run AI. And a quota is a guarantee, so you can assign quotas to users or projects. And essentially, what we then have is a concept of overquota. So maybe you've got your cluster, you've got 10 GPUs, and you've got five projects or users. They've got 2 GPU quota each, which is great. If you only need 2 GPUs, that's fine. But what happens if you need a bit more than 2 GPUs? Let's say someone else isn't using their 2 GPUs. It's a massive waste to just have those GPUs sat there doing nothing while you've got jobs queuing, and each of those projects or users would have their own queue. So rather than have your jobs queuing whilst there's GPUs free over here, we actually allow you to run over quota and utilize those GPUs until someone needs their quota back. Obviously, the larger your cluster is, the less likely that scenario ever happens. The key thing here is you end up with GPU available for your jobs to run much quicker, and ultimately you get things into the marketplace much quicker. So we've got a customer, I was talking to an automotive customer out of Scandinavia last week, and they actually have delivered 4x outcomes to their end customer as a result of deploying Run AI. So that's a really powerful use case. And actually you can see the graphs from this particular customer. So this is pre-Run AI. You can see that they've been able to get from around 5 jobs to almost 40 jobs in the space of just 9 weeks from implementing Run AI. So that's a significant increase, and you can see again from the utilization we're about 20% up to near the 80% figure. So again that 4x metric in there from a utilization perspective. And then from an organization, if you're looking at this, you suddenly see a lot more return on investment because these jobs are running a lot quicker, and therefore your models are making it into production a lot quicker. Another thing that we do that's really powerful is we have a fractional GPU capability. So again, when you're developing models, you're building your models, you might be using Jupyter notebooks, things like that, but quite often you don't need entire GPUs. But right now you're giving entire GPUs to a Jupyter notebook. And let's say you've got 40 users and you've only got 4 GPUs. If you're given an entire GPU to a Jupyter notebook environment, for example, only 4 of those can run at one time. So your other researchers are sat there, what are they doing? Having to do other things and potentially delay their work. What Run AI can do is actually fractionalize a GPU. So you can actually start running multiple workloads on a single GPU. And you can do that to a really granular level. Actually, we do it at the memory level, and so you can actually do it all the way down to 100 meg of GPU memory if you want. You probably never want to do that, but you get the idea. There's a lot of granularity. So for example, you could run 10 Jupyter notebooks on a single GPU. So again, massive increase in efficiency and productivity within your organization. And again, this is a customer who we work with. Before Run AI, they were actually assigning 1 or 2 GPUs to every Jupyter notebook. Run AI came in, and we actually worked with them to work out exactly what they need. And you can see actually the increase in the number of jobs they were able to run as a result of Run AI coming in. And we actually ended up getting their GPU utilization for the Jupyter notebooks. We found the sweet spot was actually 0.1 of a GPU. So suddenly they went from having, I think they had about 400 users there. So you can imagine how many GPUs they were needing to have all of their users accessing it at once. So suddenly just needed 40 GPUs to deliver that for all of their end users. So significant improvement from that perspective. And so if we look for what this actually all looks like when we go through the workflow, Run AI delivers this. This is how you would engage in the platform. You wouldn't need to, as I said, touch the infrastructure. Instead, what we allow you to do is essentially use an asset-based system. So we have what we call environments, and you can create these environments yourself. They're reusable. And essentially, an environment is a container image. And then a definition of that container image. So that definition is things like what tools are running in there. So for example, Jupyter Notebook, maybe you're using MATLAB or any other tools, MLflow, any of the tools that you might be using in there. You can specify those, and that's important because we will then configure the ingress for you, so you're not having to touch Kubernetes. And once you've then chosen the tools you want, so the key thing here, there's no model data here, you've got no data sets here. This is about providing you an environment with the frameworks and tools that you need to develop your model, to train your model, to run your model in production, whatever it might be. You then choose, right, how much compute do I need? So again, you can have defined blocks here. So this is like choosing an instance size in one of the hyperscalers, for example. So how much GPU, how much CPU, how much RAM. And again, you can have fractions of GPUs in here. And then the last piece is which data sets do I need? Maybe I need to attach a data set in S3 through to my container. Maybe I need to attach something on NFS. Maybe I need to clone a GitHub repo directly into that container so it's available for me as soon as it's made accessible. Run AI can manage all of that as well. So all you end up doing is choosing what tools do I need, how much resource do I need, and where's my data sets, and where do I want to store my model data. Once you've selected those things, we'll go ahead and deploy it. We pull the image for you, we will configure the ingress for you, we will connect all of the data sources for you, and you can come in here, select your newly deployed job, and then when you click on the connect option, all of the tools that exist within your environment will be available here. You'd have all of the ingress rules behind it. You can click Jupyter Notebook, you're straight into your Jupyter Notebook, and you'll find that your data sets are already there in your working folder, ready for you to start developing. And the key premise here is this shouldn't be complex for you guys, right? This should be straightforward. Your focus shouldn't be on how do I configure ingress in Kubernetes, or how do I integrate with the interface with the infrastructure. Your focus should be on developing the models and getting those models through to production as soon as possible, right? That's the primary goal. And that's what this platform is here to deliver. So take all of those complexities away. And likewise, there's benefits from the infrastructure side in that they can standardize on how they're delivering. It makes it much easier for them to support you if there's a standardized way of delivering something to the team. So yeah, in summary, the key thing here is it's a single platform for the entire AI lifecycle. You can build your models on here, you can train your models on here, and you can deploy your models on here. So you're not having to go to different tools. And that can be across multiple clusters, by the way, but still managed in that single interface. And you end up in that situation where ROI on any AI investments suddenly increase. Your GPU utilization is obviously a big part of that. And then, as I said, that zero-touch resource management for you guys so that you can actually go and utilize these platforms to do your work without any of that, those challenges and things that you don't care about from an infrastructure side of things. So yeah, that's Run AI. We've got an Echo Dot on draw later on. If you haven't entered but you want to, quickly grab the QR code. But yeah, I'm happy to take any questions if you guys have got some.
how do you handle training the model where you need to use multiple GPUs in parallel?
Yeah, so we can do distributed framework jobs as well, so like PyTorch or something like that. So you can do it there where you have multiple workers. So it depends on how your model's developed, essentially. You can also deploy a job with multiple GPUs on it. So it depends on your preference, but either or works. So for example, PyTorch, TensorFlow are all supported by RunAI, MPI, and that can all be delivered as well through the same interface.
Would you have to pre-allocate multiple GPUs for that particular project and then ensure that no other user could then use part of that resource?
Yeah, when you deploy it, the workers would be spun up and the job would typically run immediately. And so you would typically have it, you develop it separately, and then when it's ready to run, then it would just start running, obviously, and then it's based on the quota system. So how much GPU do you have in your quota, how much is available, as to whether your job will be able to run immediately or whether it's got to sit in a queue and wait for that resource to be available. Like I said, the key thing here is your queue is not reliant on anyone else's queue. You have your own queues, either on a per project basis, per user basis, however you develop it, essentially. Yeah?
Alright, thank you. So, imagine a use case where you've got a large language model for inference, right?
Yeah.
This is a customer-facing model.
Mm-hmm.
How do you scale that on?
That's a good question. So our deployments in RunAI are based on Knative, so we can do auto-scaling. So that can even scale down to 0. Obviously the fractional GPU piece as well is huge in the deployment side of things, because you might know what you'll need at your peak. What you don't want is to assign all of that the whole time, right? And again, it depends on how your model's being used and what that looks like. But being able to scale that down to 0 or maybe a single replica using just a fraction of a GPU, and then have a metric in there that triggers the additional replicas to be added.
So just to give some context to the question,
Yeah.
there's obviously the debate open source versus proprietary models.
Mm-hmm.
And people are kind of peddling that the open source is cheaper. But what kind of costs are you seeing from your customers now are using the open source models for inference, and they're having to scale that up to meet the demand?
So the open source model serving tools.
Yeah.
Like I said, I mean, we ourselves are using Knative here, which is open source. So there is things to be said for that. Those tools work, but ultimately you end up in a situation where you are reliant on community, and so support is a challenge. I think what we typically see is that when customers are building their models and training their models, they're happy to run those in open source environments and maybe even on premises and things like that. When it gets to deployment, SLAs are a lot more important, because typically there's a customer involved, whether that's internally or externally. So that's when the question then needs to be thought through in what's the best method, based on what you're doing and delivering. No worries.
Do you integrate with the most common cloud service providers and also like on-site?
Yeah, so we can deploy on all of the major Kubernetes offerings within Azure, AWS, and GCP, for example. But ultimately, our only requirement is Kubernetes. So we have our own Kubernetes scheduler that obviously understands GPU and AI workloads specifically. So we utilize that for a lot of our scheduling. But yeah, Kubernetes is the one requirement we do have, and that's the abstraction layer. I think it seems to be the standardized way as well for a lot of people who are building these AI clusters.
So we've got 40 seconds.
40 seconds, yeah.
What's your pricing model?
Yeah, good question. So there's a platform fee, or it's a platform subscription, and then it's per GPU, so nice and easy. And we don't care what that GPU is either, so they're all the same to us.
Would we make your slides available?
We can do, yeah, absolutely. I'm sure we can sort that out, right?
Yeah,
Yeah.
definitely.
Any other questions? Cool. I
Lovely.
think we're on time.
Cool, yeah.
Perfect. Thank you very much, guys.
Good. Thanks a lot, Steve. Now we're looking for our next speaker, Tanay Mehta. Tanay is a Kaggle Grandmaster. Welcome to the front. And can I put it here? Yeah. So could you plug that in? Cool, so I'm going to give you 15 minutes and then 5 minutes Q&A.
Sorry, 15
Yeah.
minutes and 5 minutes Q&A. Okay,
Yeah.
cool.
I mean, it's up to you if you want to mix it a bit. 15.
Oh no, that's okay. That's
Okay,
all right. yeah.
cool. That's a mic if you want it. Is that that should be showing, but you're not showing on the right screen. So I think you're looking to make it.
I see. It is.
Oh, sorry. Mirror. That's right. Yeah. Okay. Cool. Okay. Lovely. All right. Take it away.
Wait. It should be. Where's the on button?
Tanay. This is Tanay Mehta giving a talk about.
So, hi everyone. Thanks for coming here. So the talk is teaching large language models to infill code. Okay, and I assume, I will do a recap, but I assume you all know how large language models work in the very core of it, and that's a rather niche topic that I came across like a month ago that I didn't knew this thing really even exists. So I thought it's good to give a talk on. Anyways, a little about me. I'm a grad student, data science grad student at the University of Bath. I am a Kaggle Grandmaster, and I'm an open source contributor at big places like Hugging Face and all that. I worked at NVIDIA and at a few other startups as a machine learning engineer before. So been in this field for a while, but every day it makes me feel like I just started like this morning. Anyways, so a quick recap. I just used a few seconds that wasn't supposed to be used. Anyways, so a quick recap about large language models so that everyone here is sort of on the same page. This is the very basic version. This is the first GPT model that was introduced. I'm going to use GPT and LLMs interchangeably, but whenever I do, please just understand I mean the same thing, any large language model. So a large language model predicts the next token given a bunch of previous tokens. So a context of previous tokens, however many they can be 16 tokens, 1,000 tokens, 10,000, 32,000 tokens. So that's the past window. They predict the next tokens given some previous tokens. And when we have the new tokens, we basically compare them with the ground truth phrase. So if we have the 16 predicted tokens and we have the actual tokens that we were supposed to get the ground truth, we just compare, we compare both the probability distributions and we calculate the loss. We backpropagate, rinse and repeat. So that's basically any neural network training, and in this case, large language model training. So the main point that I want to emphasize right now is we are doing next token predictions from past to future. And I want you all folks to keep this in mind, the past to future thing, because it's going to come in really handy for what I'm going to come to next. Anyway, so that's like one simple example. If I have some context tokens like thank you for, I'm predicting the next one, which is inviting, using all the previous ones. Then I'm taking all the 4 ones that, including the new one, so thank you for inviting. I predict me, and so on and so forth until I reach the limit, or however many maximum tokens I can predict. Then I go calculate the loss, update the gradient, and do this thing all over again. So this is, I hope it's all clear. Does anyone have any doubt on this part? Probably not. Okay, cool. So now there's the curious case of code infilling. So how many people have here used GitHub Copilot? Right. So you may have written a function definition, a function signature, and the code inside the function, and you wanted to generate the docstring of the function, right? You started writing, and I'm talking specifically in Python. You started writing 3 codes, and then Copilot basically predicted what the doc string is going to be. Now, if you think about it, that's actually very funny, and I'll take an example. So this is a basic Fibonacci sequence program in C++. I have the code before it, before the actual Fibonacci sequence, and the code after it that runs it. And this great thing is basically what, I call it generated, you can also call it predicted, but this is what the large language model, in this case GitHub Copilot, predicts or wants to write. But there is a big thing, if you think about it enough, you will realize that it's not following the general paradigm of a large language model, because you're not predicting the future, you're predicting something in between. This is called infilling. You're filling stuff in. And the more you think about it, it starts making a little less sense, because you're given the past and you're technically also given the future. You want to predict something that's not that much into the past. And it doesn't make a lot of sense. So how does a model like Copilot, or how does any other model do this? And yeah, so how do we infill? So because large language models only generate the next token given some previous tokens, how do they generate something in between? And that too so accurately, because Copilot has been pretty accurate in most simple cases. So maybe one of the things that can come to your mind very like out of the box is prompt engineering. You define a really nice prompt, the system prompt. In this case, I defined it in the OpenAI playground, and I'm just defining a prompt saying that there is a new token called complete here. Wherever I put complete here in the input, you complete whatever comes there. And then I'm going to provide a function. So that's the same Fibonacci sequence code that I just showed you. And in the place of the recursive code, there is the complete here token. And we basically so we are basically giving it as a prompt. So we are trying to solve this problem using prompt engineering, trying to not do any analytical, like trying to not alter the training of the model, but instead just giving it all as a prompt problem. And we have seen in the recent papers and recent researches that large language models, especially the bigger ones, or the mixture of expert ones, they are really very good at something called in-context learning. So in-context learning is basically the model learns without the gradient update. It learns given the prompt. Technically it doesn't learn anything because there's no gradient update, but it sort of figures out. So we give a system prompt and we define a token, and we are like, wherever this token is, you complete the code. We use that token in our input, and when we run it, it does work, as you can see. And I ran it and it did work. The OpenAI did generate it in the complete here, but there are a few caveats to this. So, I mean, why not use this? Let's just end the presentation on the next slide, and we all can go home a few minutes earlier, right? That's the end of the presentation. But there is a few caveats to this. The first of all is it doesn't work very well in very large, very complex tasks, right? Because it starts hallucinating, and that's, I mean, I'm technically encroaching on the second point, but it starts hallucinating. And then there are these two big problems. LLMs are not very deterministic. So given your settings of temperature or other values, other hyperparameter values, they may give different outputs for the same input to run 2 different times. And you don't want that in production. I mean, if GitHub Copilot had that, we would all have had a very bad nightmare using it. And then the other problem, and it's a much bigger problem than many assume, is the problem with the token cost. Because every time we are trying to run it, we are passing, if you see here, we're passing a system prompt every single time. No matter what, we are always passing this. Without this, there is no meaning of complete here. So we are passing a system prompt, and it doesn't look much right now, but when you run it again and again, because if you think about how Copilot works, you start writing something, and Copilot is running all the time in the background. It's always predicting the next sentence of whatever comes next. And if you think about it, it's a lot of requests every second, or every time you do a keystroke, it sends a request. And these tokens, these few tokens, they add up in the longer run. So it's going to incur more and more costs when you're doing this again and again. So clearly, prompt engineering doesn't work. What do we do then? Well, enter OpenAI. I guess we can use this a lot of times, this title, enter OpenAI. So they came up with this very nice paper called Efficient Training of Language Models to Fill in the Middle. That was a 2022 paper, so it's not that old, or I guess anything that's more than a few weeks ago is very old in these days. But and it may sound very like it's an OpenAI paper and it's pretty long, so it may sound like, oh my god, they're gonna like introduce some groundbreaking architectural changes. Actually, no. So what they are basically doing is they're essentially like, instead of prompting or like changing the architecture of a large language model, they just change the data, and that's a really smart way of approaching things. So instead of doing like maybe new attention modules or stuff like that, they're just like, hey, we just change the data. So they add 3 new tokens to the data, the tokenizer and the data as a whole: pre, suff, and mid. So prefix token, suffix token, and middle token. So yeah, that's it. So whenever you are tokenizing your data set, they take a batch of data and they add these tokens randomly in between. And it's a very random process. You can describe however many times they do it. You can do it 50% of the time. So if you have 100 samples, 50 of them will have this transformation. I'm going to touch more on that, what it really means. And yeah, that's it. So this is what it means. So basically, the prefix token that I talked about, what they do is, let's say you have a sentence, right? And you can divide that sentence in 3 parts. You can randomly have a middle part of the sentence, then you have a part that comes before it, the prefix part, and the part that comes after it, the suffix part. So they randomly, and that's exactly how their code base works. They're randomly taking a sentence of tokens or a sentence of words, and they're dividing it into 3 different smaller sentences, and they're adding these tokens in between. So prefix, and then the encoded version of prefix, which is the tokens, then the suffix token, the encoded version of suffix, and the middle one. So as you can see, they're sort of changing the order. Generally, how a sentence is that prefix, middle, suffix. That's a normal sentence, right? They're basically shuffling the last 2 bits. So instead of having prefix, middle, suffix, they're doing prefix, suffix, middle. This is also called PSM transformation. So that's one of the things they introduce in this paper. Yeah, so this is called prefix, middle, suffix, PSM. There's another one called suffix, prefix, middle. In practice, you can use both of them at the same time. As in, like, sometimes you will use PSM, sometimes you will use SPM. I'm going to touch more on how they do that. Or you can use just one of them or whatever setting you want. So, little meme, don't change the model, change the data. Okay, so let's touch up on the FIM algorithm and how it does inference. So in the middle algorithm basically is like, I didn't even need to write it in Python because it was so simple I could write it in slides. You randomly select 2 indices in the sentence called boundaries. So indices are like 2 points in the sentence. So if your sentence has like 15 tokens, maybe first index will be 7, the other one will be 10. So these are like 2 indices. So if you have 2 indices in let's say if you have like 2 points in a line, you basically divide that line into 3 parts, right? If you put 2 points in a line, the line is divided into 3 parts. That's basically the same thing, but with a sentence of words or tokens. So all tokens until the first boundary, and those like the indices or the boundaries, they are chosen randomly. As long as they're in the range of the sentence we're talking about, they're chosen randomly. That's literally what they're doing. I'm not even making this up. All the tokens until the first boundary become the prefix. So you can sort of mentally imagine a line with 2 dots in between that divides that line into 3 parts. The first part becomes the prefix. Yeah, you're right. The second part becomes the middle. And I mean, technically, between the first boundary and the second boundary, everything becomes the middle, and the remaining of it becomes the suffix. And so I think most of you can see where this is going. They just then take this and they shuffle it according to what we need. So this is like a very neat example. That's the same Fibonacci one, the code that I touched up in the beginning, but it's using this transformation. So this is the prefix part. This, as you can see, this is where we needed to have the Fibonacci, the recursive case, but they took it and they put it down there. So, and the rest of it is the suffix until here. So prefix, suffix, middle, PSM. And this is how they train the model. In inference, they will just remove this thing, the last one, because that's what the model needs to predict, they just give this middle token to tell the model that, okay, you need to predict everything that comes after this part. So that's how the inference works. Basically, in inference, we don't give the middle part because that's what we want to predict. We just give the prefix, the encoded version of prefix, suffix, token, the encoded version of suffix, the middle token, and everything else the model predicts. And that's it. This is exactly how GitHub Copilot works. I mean, on top of other things, this is what they do every time you're writing some code. And that's what Copilot is doing in the backend. So, but what about non-infilling tasks? I mean, yeah, sure, you can do that, but most models these days, they can do both code generation and text generation. And text doesn't work like that. You don't need to predict the middle part of a text. That's not what an LLM is supposed to do. So this is, I think, the biggest benefit of this is that there's something called FIM for free property, and that's what they showed in the paper, is that let's say they have 10 million data samples, and on 50% of them, they do this FIM transformation. The other 50% are just normal. What they saw is that when they train the model on some data samples with the transformation, some without the transformation, the model learns the FIM property, and it also learns the general large language model property. So it can generate text like any other large language model, but it can also do the infilling, the fill in the middle thing. So the AR here means autoregressive. So in training, some data percentage will be transformed using FIM transformation, and I'm not trying to oversimplify this. The best code, there's not much code base of it on the internet anyways. I'm trying to add one, and the only code base that there is literally doing that. They're just using np.binomial and they're basically doing that. So some percent of the data will be FIM transformed, the others will not be. And the model will learn to do both fill in the middle thing and normal autoregressive modeling. And this is why they call it FIM for free, because the model is actually doing what it was supposed to do. Basic text generation, next token generation. But now it's also doing the fill in the middle thing, which is very important when you're dealing with code tasks and code generation. So you're essentially learning the FIM skill for free. That's why it's called the FIM for free property. And that's the graph from their paper. So the yellow one, 0.5 means 0.5% or 50% of the samples are transformed using this FIM dataset trick, and 0.0 means none of them are. So when in the case of 0.0, it's the basic large language model pre-training, nothing fancy. And the performance is practically the same. So on both of them, in language and code, the performance is the same. So you don't get any performance loss, but you learn one very important trick for free. So yeah, practical examples. The fill in them, if you want to take pictures, you can. I will share the slides later on. But this is the paper, the original paper. They don't have any code things associated with it. I'm adding an FIM example and a pipeline to Hugging Face transformers. If you want to follow along, you can follow this PR once it's merged. It's great. Hugging Face's big code star coded model supports fill in the middle thing out of the box. So you can see the docs and they do it. And so does Meta's Code Llama. So yeah, both of them basically support it out of the box. So yeah, I have like 3 minutes remaining. So any questions?
Well done for the presentation. A bit too much for my age and this time of day, but well done. So you did mention that they are throwing in the tokens randomly. I'm thinking about, can it be completely random because we are going to lose the context? Like even if you think about the text, if I have a sentence that I'm saying, camel is a big animal and you cannot fit it in your pocket, if I just move that to the end of 10 other sentences that is coming, it may change the meaning. Same for the code.
So it's not going to change it. It's not going to change it. It's not going to throw it like after 10 other sentences. Everything will be context aware. So so all the transformation will be for one sentence or one paragraph.
But when we are talking about the code, we don't have sentences, isn't it? So are they using the context of function possibly or some?
So how I'm doing it like in code is that taking every single example, which is one sentence, whatever the length it is, and doing it to every single sample, but randomly. So like 50% of the samples may have this, 50% may not.
Okay, I was wondering more in the context of code and how
So
Copilot may have done it.
So Copilot, so when Copilot, I'm not sure exactly what dataset Copilot was trained, but if you're talking about any code dataset big enough, I think the most popular one is CodeParrot, which has all of GitHub's repositories that are public. It's huge, it's a 1 TB dataset. So what they do is, in the dataset itself, and this problem really comes down to the dataset. So in the dataset, they have, each row has, among other things, one function, or however they decided to basically divide the code discrete. So one function, and we do it for every single sample. So you can call it like one file, for example. Every row has all the code for one file from the GitHub, and we do it in that single file. Yeah.
Do you think a base model was used in like generating the dataset for fine tuning for Copilot? Because I think like it must have been like so much samples and how it's labeled. Like, was a base model used or was it manual? What do you think?
I mean, I can't comment with specificity on that because I haven't read much about Copilot, but I think they use something like all of GitHub's code and like stuff like that, all public GitHub's code, and I think one of the recent ones, because I saw GitHub engineering blog, one of the recent ones, they basically tried using something like that.
I mean, for the fine tuning, it is like.
For fine tuning for what? Because this is pre-training. This is not, this works, I mean, you can use it in fine tuning, but it will be a continual learning problem. That's
So it doesn't need fine tuning like for Copilot, it's just generating and then it's fill in the blanks and apply.
yeah, so this is the pre-training phase. This is like not the fine tuning phase. You do it in the pre-training itself.
It works, not in the
Yeah, it works out of the box, yeah.
Alright.
Yeah, please, you. Yeah.
Great. Can you please explain quickly what is the intuition behind this PSM transformation and why does it work?
So, I mean, neural networks are sort of a black box, so I may not be able to give the 100% correct answer, but I think from how I understand it is that if you give enough samples, so right now 50% of samples transformed using FIM sounds a very small thing, but when you give it 1 million samples, that means 500,000 samples. So just the way how model learns, normal autoregressive modeling, it also learns this sort of thing. So that's I think why it does that.
Cool, there's no more time. No more time for Q&A? No.
Okay, so you folks can like ask me a question after this because like there's another session after it. Yeah, I'll be up there so you guys can attack me.
Cool. Thank you. Thanks a lot, Tanay. So we're looking for Saurav. Hey, cool.
Do you have a Type-C adapter?
Yep. It's in my pocket.
Hello, people. Tech problems. I apologize.
So this talk will be our final talk for the day. So that's like 15 minutes and then 5 minutes Q&A. And then we've got like a 5-minute demo from like a startup. And then it's basically like networking time after that. But actually after the 5-minute demo, there's the raffle. So I'm going to do the raffle stuff. And there's the chance to win some things. So it's still not working.
You want me to just share the link with you?
Yeah, sure. So in that case, we're going to use mine. Okay, so that means you're not going to see this.
It's fine. for one of us.
Okay.
There we go.
So yeah, I guess.
Yep.
Can you hit that?
Okay, yeah. Okay. Sure. Okay. Hello, people. First of all, let's address the elephant in the room. So, people who have seen this, I am the same person. I just woke up one day and decided to not shave. So, I'm not impersonating to be someone else. I'm still the same person. But yeah, hello. So, my name is Saurav. You can call me SV, so just the letters S and V. I'm a research machine learning engineer by trade. I work on geometric deep learning and self-supervised representation learning. I will not be talking about any of that today. I will be talking about efficiently fine-tuning large language models. Why? Because I think it's something truly beautiful and we don't understand why it's happening. Therefore, I would like for more people to know about it. I do a lot of open source work. I've contributed to TensorFlow, PyTorch, Parallel, NumPy, JAX. I used to work full-time at Weights and Biases and Ricochet. So yeah, that's my background. Okay, so I usually give this for like 40 minutes. I'm trying to do this in 15 minutes. If I'm talking fast, that's why. If you have any questions, feel free to stop me in the middle. Hopefully we get through the first two things. Third and fourth are just extra bits on top of it. But yeah, so let's think about what the traditional deep learning pipeline is. Your company is able to get some data. It's typically in hopefully gigabytes or terabytes of scale, and using that you pre-train one large model, right? It's one large data set and then you have one corresponding large model, and depending on what you want to do, you will fine-tune multiple models on top of it, right? An example in code would be, so for example, if you have a pre-trained board model and you want a different model for sequence classification or question answering, you would fine-tune multiple models using that one pre-trained model, right? So you pre-train first and then you fine-tune. But what I'm claiming is that fine-tuning isn't really an ideal way to go about doing things, because if you think about it, you are using a smaller data set, you are changing possibly millions and billions of parameters. So using a smaller data set, you are changing all of those parameters itself. But what you want to do is, you already have one pre-trained good working model. You just want to make it work for your particular use case. And of course, fine-tuning itself requires training, therefore it depends on your data set size. So it grows almost linearly. So there were some possible solutions that people came up with, which was, okay, how about we only like learn the last 5 layers, last 10 layers, last 15 layers, or how about you learn another smaller model on top of it, place it on top of your pre-trained model and just use that. Those are viable solutions. However, when used in real time, they have latencies or they are just not as good as just normal vanilla fine-tuned models. Now that's where the concept of intrinsic dimensionality came about. It originally originated in like 2018. Some people from Uber AI Labs came up with it, but essentially this is the crux of my talk. So what they discovered was, you don't actually need to calculate the gradients across all the dimensions. So for instance, I know maybe all that your company does is it classifies whether a given image is hot dog or not a hot dog. You have a 1,000 neuron model and you're trying to train it. So the typical paradigm involves that while training, you compute the gradients across all 1,000 parameters. What they found out is you don't actually need to do that. So if you see the last graph, the numbers are 0, 10, 30, 40 and so on. At some point, if you only compute the gradients across 10 dimensions, the performance is as same as training the whole model. So there inherently lies this smaller number called the intrinsic dimension, at which point the performance of your model peaks. Now that should be truly remarkable, right? Because I know BERT might have millions of parameters, and I'm saying you only need to compute the gradients along 50 dimensions, and that's the same as working with millions of parameters. Yes?
Okay, out of 50 dimensions, how to choose 10?
Yes.
Which 10?
Yes. Good. What the researchers did is that they took randomly, they randomly selected some subspace, very much, yes, randomly, and it works somehow. Why? Well, we'll ask mathematicians. But yeah, so the typical paradigm, the typical paradigm is you compute the gradient across all of the dimensions. What I'm saying is, don't do that. Just pick a randomly allocated smaller subspace of 16, 32, whatever, and the authors claim that it will still have the same performance as training across all of them, and they proved it empirically as well. And this is way back in 2018. Yes. So, well, this is code. I don't think we'll have time to go over, but ideally, this is what you want to do. You have some optimizer. And then before you compute the gradients, you take some random subspace of it. In this case 16, but of course 32, any power of 2 somehow works. I don't think that's readable at all, it's good. But yeah. Also, let's take a moment and think about like why fine-tuning works at all, right? Because you're trying to like update millions of parameters with only thousands of samples. Surely there is something wrong with that ratio there. How does that even work? And what the authors claim to say is that if you look at this with the lens of intrinsic dimensions, there is actually a way to show like why it works. And they showed empirically that if you pre-train your model on a big enough data set, this property of the landscape, right, this intrinsic dimension gets smaller and smaller and smaller. That's why fine-tuning works, because you have pre-trained the model, you only need to update some of it. So that's like one way to explain why fine-tuning works. And in fact, the bigger your model is, the smaller its intrinsic dimension is. Now, this is the main thing which has been all the rage, LoRA and adaptation of large language models. Essentially, if you already have some pre-trained weights, what you want to do is train two smaller matrices A and B. And again, just think of these as two very small sparse matrices, and they sort of thin out in the middle. That thinning parameter R is the aforementioned like rank, right? And what we're trying to do is that we're not trying to update all of the parameters, we're only trying to update some of them. And the way you do that is, when you update the weights, what people usually do in gradient descent is using some learning rate, some normal optimizer, you change the weights. But instead, the way you change the weights is just you compute the product of those two matrices, and those two matrices are what you train over time. And again, they thin out in the middle. That thinning out, that R parameter is of importance here. So now I'll show you like some actual results, because I know I would not believe it if someone said that to me. And this is all possible because of great open source work done by Hugging Face. Two people I would like to mention, Saurav, Mangulkar, Saik Paul, and that's me right there. But yeah, all of this work is possible only because of that. And the code itself is simple enough. So you create this configuration file called the LoRA config. You specify your rank, in this case 16. Then there are some other parameters you can modify, but then that's it. You just put in that model, train it, and then somehow it works. I think this was, this was a vision transformer. So this example is on a vision transformer image classification task across 100 classes. The number of parameters is 86 million of the original model. With a rank of 16, all that we are updating using this method is 667,000 weights, which is 0.77%. Yes?
Does it matter if you choose a different set of parameters?
Different setup?
The random projection in
Yes.
a smaller set of dimensions.
Yep.
Does it matter if you choose choose a different cell, do you converge to the same thing?
Yes, so the authors of the paper ran it across multiple random seeds, therefore meaning it was different random subspaces, and all of them had the overall the same results.
And how did you implement it in the library? Did you?
You just change the random seeds. So, I mean, I can show you the code afterwards, but it's just randomly taking like a normal subspace. So, by only taking 0.77% of the weights, I am claiming that the performance will be good enough. Now, 96% on the training side. I would consider that to be good. Now, this is why you should focus on this, because if you are working on a company which is trying to maybe train LLMs, this saves you a lot of compute and a lot of time. You only need to update 0.77% of the weights, and you are still somehow getting overall the same results. And again, the throughput does not change, the runtime does not change. It is still inherently the same model, just you need to train it less. Now there are some open questions. Of course, does the fine-tuning dataset size matter at this point? Because apparently if you choose a rank small enough, it works. So does the fine-tuning dataset size matter? And if it does, is there a dependency between the dataset size and the rank? I don't know, if you have a dataset size of 50,000 and a rank of 16, does that scale to 100,000 and 32? Right? There are questions like this which needs to be answered. Or I don't know, and if it does matter, what is the equation? Is it linear, quadratic, who knows? And how do you scale this? Some of these questions have been answered in the past few months with people making lots of versions of LoRA, some of which we might cover if we have the time. But yeah, okay. Oh, we do have the time. Lovely. One of them is adaptive budget allocation. So if people remember what CNNs essentially do, right? There's this one famous image which I particularly have in mind, and that is like the initial layers of the CNN identify the overall structure of the model, right? And as you go deeper, they are responsible for identifying the texture, right? One of the sort of the limitations of LoRA is the rank is the same throughout, right? So you're sort of giving the same weightage to all of the layers, which isn't actually true in most model architectures. So how do you adaptively allocate the budget? That is what the question here is. And of course, if you allocate more budget to the matrices which matter more, the overall model performance will be better. Now, how do you choose those? Well, yes. So people who somehow remember linear algebra, I do not, but like that's the equation right there, make sense of it. They are the left and right singular matrices, and delta contains the singular values. Please go through the paper if you are interested in this. I do not know enough, but yes, the results. LoRA is performantly better than most LoRA variants. So adaptively allocating the budget does work. How? Look at the math. I don't know. One final thing which has came up recently, which is LoRA. I particularly find this like the most amazing paper ever, because what they try to do is that they train an already quantized model. So I'm saying already, you know what, just like train 0.77% of the model. But what if the model originally itself is already quantized? So this is, I don't know, possibly how far we can go. I'm sure someone will come up with something else. But yeah, the main key contributions of this paper is they introduce a new data type, which is the 4-bit normal float type. Essentially, it overcomes the drawbacks of the float 4 type. It's essentially normalized, so you don't. It's easier on the GPU. It's double quantization. So the model that you're using to fine tune it itself is already quantized. So you're quantizing a pre-quantized model, and then they use what's called a paged optimizer, which is just some fancy engineering trick. Now, if all of this sounds like an engineering trick to you, that is essentially what it is. People with lots of GPUs came up with this idea. So, yeah. Do I have the results of this? Okay, no. But yeah, it's simple enough to implement in code. Hugging Face thankfully has like very nice wrappers around this, so you just need to specify which data type you want to use, in this case NF4, which optimizer you want to use, in our case the paged version of Adam, and you just put into training and it magically works. That was a lot of fast speaking. Oh yes, okay. We did in time. Any questions? Can I have some water, please? Yes.
Thanks for the presentation contribution. It's really amazing because I feel the pain of not having an H100 in hand and trying to do
Yeah.
stuff. And you can do it thanks to this. If you want to go back to the basic, how would you compare LoRA to transfer learning that we used to do? And you mentioned that around the convolution nets too.
Yeah.
It's almost we are doing the same thing. Is it rethinking the same thing just for much bigger architecture and reinvent the wheel? Say, okay, now I realize that end layers are more important, so let's give them more weight. Or is there something new here?
Okay. Overall, what we are going for is the same thing, but it is slightly different. So if you if I can scroll back to the original LoRA picture, in transfer learning, what we're essentially trying to do is we don't change the architecture of the model, right? The weights still remain the same. However, in LoRA, we do change the architecture. So the shape of the weight matrix itself changes.
Oh, okay.
Right? The shape of the weight matrix itself changes. So although we're trying to go for the same thing, we are somehow inherently changing the shape of the weights. So that's like one key difference between traditional transfer learning and LoRA. But yeah, essentially we're going for the same thing. Any other questions? Going once.